This is a direct current tutorial presented by DSHLTB. Hello, welcome to a new tutorial presented by DSHLTB. In this tutorial, we're going to see direct current. Now, direct current is a chapter which is involved in our homes in order for the production of the different appliances. Inside the appliances, you can see that appliances can be rated as current of 5 amperes, voltage of 10 volts, and power of 100 watts. So all these are the values which are circuit quantities used in order to rate certain appliances. Appliances such as lamp are very important in order to lighten our homes, and these are all based with respect to direct current. In our phones, we have resistors, capacitors, inductors, which are all working with the principle of direct current. So the chapter is going to involve with direct current principles. So to start with, we're going to start with the different physical quantities involved in this chapter. And the physical quantity involved in this chapter are going to be number 1 with the charge, number 2 the current, number 3 the current density, number 4 the voltage, number 5 power, with number 6 electric energy. Now, what is the charge? This refers to a quantity which is a fundamental essence in the existence of atom. So the charge is given as the number of the charge is normally given as the number of electrons, of conductive electrons, times the times the fundamental charge E, and this E is the charge of an electron. So the charge of a material will be equal to the number of conductive electrons times the charge of one electron. The charge of one electron is given as negative 1.6 times 10 to the power negative 19 coulombs. So now, N here is a number of conductive electrons in material. So at times we can be given the density, the number density of electron. So Q here will be equal to N, which is going to be this N all over V times V. So because N all over EV, this is going to cancel. This N here just equals to N small n all over big V, and this is considered to be the number of electrons per unit volume. So when you are given the number of electrons per unit volume and asked to find for the charge, it will be equal to number of electrons per unit volume times the charge of one electron times the volume of the conductor in which you are asked to find. So now let's visualize what's the current. The current refers to the rate at which charge changes with respect to time, and this rate at which charge changes with respect to time is the rate of change of charge is usually due to the flow of electrons. So the rate at which current the charge change with respect to time is mostly due to the flow of electron from the negative terminal of the battery to the positive terminal of the battery. Now we need to note that conventionally current is taken from the positive terminal to negative terminal, but the positive charges do not flow, which are the protons, do not flow, but instead the electron which flow from the negative terminal to positive terminal. So by convention, we say that current move from positive side of the battery to the negative side. So now let's visualize what happens in case of conductors and insulators. Normally, electrons exist in valence shell zone, and there also exists a conducting zone inside atoms. The valence shell zone is a zone where the electrons are found closer to the atoms, while the conducting zone is a zone at which the electron can be used in conducting current. Now for conductors, we see that the distance separating the distance and thus the energy separating the conducting zone from the valence shell zone is smaller compared to insulators. So small energy which comes from the potential difference can be required to emit the electron to the conducting zone for it to conduct current. While in case of insulators, we see that the energy which should be supplied to the valence electron for it to enter into the conducting zone is very large. Since this energy is very large, the potential difference will not provide the sufficient energy for the electron to move from the valence zone into the conducting zone for the electron to be conducted. This is why insulators do not conduct current. It's due to lack of current, due to lack of electron in the conducting zone. So this I is equals to the Q all over dt, because what initially defined as the rate of change of charges with respect to time. And now if the current is constant, it implies that it is going to be the charge all over the time. So now we have again here, we've initially said that the Q is equal to the n here, and this n here is the number of charges. This n here is number of electrons per unit volume, E, which is the charge of one electron, times V. So this formula was already found, and this V here we say that is equal to AL. So from this diagram here, we visualize that we have this length here, and we have current flowing opposite direction to electron. So if you are to find for current is initially dq all over dt. Since current is equal to dq all over dt, you can substitute for NEV, which was the value of the Q we've initially found. So we're going to have current is equal to d of NEV, but the volume is equal to the cross-sectional area times the length here. So we are going to substitute here. We are going to say d of NEAL all over dt. Now we need to know that N, which is the number of electrons per unit volume, E, which is the charge of an electron, and A, which is cross-sectional area, are all constant with respect to time. So they're going to move outside of the differential. So we're going to say ENE A d of L over dt. It is only L which changes with respect to time, and that L change, the L over dt, is given as the velocity of electrons. So the current vector is going to be equal to the NEA velocity vector, and this N here is going to be the number of electrons per unit volume. So now the current density is defined as the current flowing in a material per unit area. So this current density is given as J. This current density is given as J, and this J is equal to I all over area. So substituting the value of I, which is never here, which is NEAV, into this formula, we are going to say that J vector is equal to NEV nev vector. So now voltage, let's visualize voltage. We need to know that by definition, voltage, this refers to the work done. Voltage or potential or electric potential or potential difference is defined as the work done required to move a unit positive charge from the positive terminal of a cell to the negative terminal. This is the voltage. The energy, the work done per unit charge, per unit positive charge, in order to move that positive per unit charge, in order to move a positive charge from the positive terminal of a cell to a negative terminal. So V is equals to W all over Q. This is why current is always moving in the direction from positive to negative, because by convention, when you want to take the motion of particles in a system, we always consider mostly the positive charges and not negative charges. This is because by convention. Now the electromotive force, this refers to the ability of a source, a cell or battery to cause charge to flow in a conductor per unit time. So this is the electromotive force. Now let's say that you have a circuit as such here. So normally with an ideal cell, an ideal cell is going to produce only an electromotive field. But with a real cell, there is an EMF which is produced, and that real cell has a small internal resistance. So now the power input, the EMF, the efficiency of a cell is going to be given as the EMF output all over EMF input times 100%. The EMF output is going to be the EMF input minus the voltage is going to be lost via the internal resistance, which is minus IR, divided by the total EMF produced by the cell, so divided by IEN. So N efficiency is going to be EI input minus IR all over E input times 100%. So now let's visualize the power. The power refers to the rate of change of current the rate of change, the rate at which a circuit element dissipates energy per unit time, or is a rate at which a circuit element store energy per unit time, depending on if the property of that circuit element is to store or dissipate energy. If it's a resistor, power is going to be defined as the rate of change of the rate at which a circuit element dissipates energy per unit time if it's a resistor. And in case where it's a capacitor, the power is going to be defined as the rate at which the circuit element store energy per unit time. So this is the power, and this power here is going to be defined as P is equals to IV. So now let's visualize here the next part. So now electric energy. The electric energy, this refers to the work done by an appliance in order to resist the current flow through it. So the work done in order to resist the current flow through it. So this are the energy which can be stored inside an appliance, a circuit element. So these are the two main, or it can be referred as the beneficial energy produced by an appliance once current flow through it. So this is the electrical energy. So the electrical energy is given as the power times the time. So now P is the power and T is the time. So power is given as IV. So electrical energy is also equals to IVT. So now let's find the efficiency of a circuit element. Initially you have found the efficiency of a cell, and now let's find here the efficiency of a circuit element. Efficiency of circuit element is going to be equal to energy outputted all over energy inputted times 100%. Now the energy output is going to be I out V out times time. Energy input is I in V in times time. So when you substitute all it, we are going to have I output V output all over I input V input times 100%. Now we know that in most circuits the I input is mostly equals to I output. So if you have the I input being equals to I output, like in series, like in case of a circuit which is in series, then we are going to have V output all over V input times 100% as being the efficiency. Now if the circuit is in parallel and we are going to have V input is equals to V output, it implies that the efficiency is going to be I output all over I input times 100%. Now let's visualize the different circuit elements involved in direct current. The first circuit element is the resistor, and the resistors are going to respect the Ohm's law. The Ohm's law states that ohmic conductor, so the resistor, Ohm's law states that the current through an ohmic conductor is going to be directly proportional to the voltage or the potential difference drop on that ohmic conductor, provided that no temperature change is at constant temperature. So this is for Ohm's law. Ohm's law states that the current on an ohmic conductor is directly proportional to the voltage drop on that conductor at constant temperature. So V is going to be directly proportional to R. It implies that V is equal to K times I. And now this K here is going to be the resistance from experimental analysis. So from experimental analysis we have this graph here. So the graph is directly proportional. So now in case of thermistors and light dependent resistors, we see that as a resistance, the resistance is going to reduce. In case of thermistors, the resistance is going to reduce as the temperature increases, and this is by following this formula here. So we are going to say that R is equals to R at the resistance at 0 into 1 minus alpha theta minus beta theta squared. So this is a formula of resistance respecting the inverse square law. So it's going to be inversely proportional here in case of thermistors. But we need to know that this beta theta here is approximately going to be equal to 0 in most times. So the formula which is used for thermistor is R equals to R at 0 kelvins into 1 minus alpha theta. Now this formula states that what? If temperature increases, the resistance is going to reduce from the initial resistance, which is going to be equal to the resistance at 0 Kelvin. So R0 here is a resistance at 0 Kelvin. The more the temperature increases, the more this factor is going to reduce 1, and this is going to cause the resistance to be lesser than the resistance at 0 Kelvin. So you see that the thermistor have a lower resistance the more the temperature increases. Now for ohmic resistors, this formula mostly applies, where R is equals to R0 into 1 plus alpha theta. Now for ohmic resistors, you need to know that most of the time when temperature increases for ohmic resistor, the resistance increases. And there are two different reasons for this formula to differ for thermistors and ohmic resistors. Now for ohmic resistors, we see that as temperature increases, resistance increases from from the 0 Kelvin resistance. So this is 0 Kelvin resistance. So as temperature increases, this factor is going to increase. So resistance is going to increase from 0 Kelvin. And now let's visualize the reason why here in thermistors there is a decrease in resistance as temperature increases, while in ohmic resistors the increase in resistance as temperature increases. Now in case of thermistors, you need to know that as temperature increases, the resistance reduces just because there are more electrons which are moving from the valence shell zone into the conducting zone for them to conduct more current. So this is why the resistance reduces. The resistance reduces because more electrons are moving from the valence shell zone into the conducting zone for them to conduct current as temperature increases. While in case of ohmic resistors, we see that as temperature increases, it's going to cause the more vibration of atoms, which is going to oppose the flow of electrons and thus causing resistance to increase. Now this resistance increase can also be due to an increase in resistivity, because you need to know that the R here is going to be equal to resistivity A all over L. So the effect on the R is mostly the effect on the R via the temperature is mostly on the resistivity, and that formula on resistivity is given as resistivity is going to be equal to resistivity of the at temperature 0 Kelvin into 1 minus P plus alpha theta. So you can place it here. So when placing it here, we are going to have resistance is equal to resistivity at 0 Kelvin times area all over L into 1 plus alpha theta. So now let's visualize the power and energy of a resistor. The power of the resistor, we normally know that is given as, the general formula for power is given as IV. Now, but we know that via Ohm's law, V is equals to IR. So you can substitute V here. We see that power is equals to I squared R, or power can be equals to V squared all over R. And the energy of resistor is going to be normally given as IVT. When we substitute, you're going to have E is equals to I squared RT, P is equals to V squared T all over R. Now let's see resistors in circuit. When resistors are in circuit, we see that the voltage drop on this resistor 1 is going to be V1, and the voltage drop on this resistor 2 is going to be V2. So the total voltage is going to be equal to V1 plus V2. But the current is going to be same in R1 and R2. So it implies that what this V, we need to know that V is equals to IR. So V here is going to be IR total is equals to I1 R1 plus I2 R2. But we know that in this circuit here, I1 is equals to I2, which is equals to I. The same current pass through I1 and R1 and R2. So this IS, I and IS. So you can cancel all through with I. So you see that the R total, the total resistance when resistors are in series, is the addition, the sum of the resistances. So R1 plus R2. This is the total resistance. Now, in case where you have resistors in parallel, as shown here, we see that what? We see that the V1, the voltage drop on this one is going to be equals to the voltage drop on this one. So V1 is going to be equals to V2. And we need to also note that the current here is going to split into two main parts as being I1 and I2. This I here, we need to know I is equals to V all over R. So V all over R total here is equals to V1 all over R1 plus V2 all over R2. So now we need to know that this V1, we said that V1 is equals to V2 is equals to a total voltage when they are in parallel. So V1 is equals to V3 equals to V2. So when we substitute all this, we see that all these are going to cancel. So 1 all over total resistance is equals to 1 all over R1 plus 1 all over R2. The inverse of the resistance is the sum of the different inverse of the different resistances. So solving the above equation, we see that the total resistance will be equal to R1 times R2 divided by R1 plus R2. Now let's go to the next circuit element. That next circuit element is called capacitor, and the capacitor is used to store electric charges and electric energy. The main constant which is involved with the measurement of capacitor in capacitors is the capacitance, and this capacitance is given as the epsilon 0 epsilon r a all over d. This capacitance also given as Q all over v. So now the energy and the power of capacitors has already been filed in the chapter on capacitors, and we said that it's going to be equal to E equals to half CV squared when the voltage varies. It's going to also be given as energy stored equals to half Q squared all over C when the charge varies, and it's given as E equals to half QV when both the voltage and the charge vary. And we initially said that the energy stored is always half of the total energy, just because some energy is lost via resistance and some energy has been lost via the emission of electromagnetic waves from capacitors. The total energy given as QV, Q squared all over C or CV squared, but the energy stored is half of this energy for capacitors. So now the power is given as dE all over dt. So now the energy is half CV squared. When we substitute, we see that it's going to be half C dV squared all over dt. So now we need to know that in this case here, the voltage varies. So the power when the voltage varies is going to be dV squared all over dt. So we are going to differentiate differentiate of f of g of the function of function. So we differentiate interior, we are going to have dv2v, and we differentiate exterior, we are going to have dv all over dt. So we are going to say that power is going to be cvt dv all over dt at certain time. So now, in order to explain the last formula, this last formula here, we will use a simple example. Yet let's say that provided that you are required to calculate the power of a capacitor at time 5 seconds. If you are to calculate the power of capacitor at 5 seconds, it will be equal to the power of the capacitor at 5 seconds will be equal to the capacitance, which is a constant, the voltage of that capacitor when it's at 5 seconds, and the rate of change of the voltage with respect to time at t is equals to 5 seconds. So now when the charge varies, the formula will be Q squared all over 2C as being the energy. So when you substitute, you are going to have the formula. This is going to be the formula of power. Power is equal to QT all over C dQ all over dt. And when both the charge and the voltage varies, you are going to have the formula of energy as being half Q V all over dt. So now here, as you are going to differentiate, you are going to differentiate function times another function. So we are going to differentiate it. We maintain this one, differentiate this other one. So it's going to be half into Q dV all over dt, plus we maintain this one, differentiate other one, V dQ all over dt. So the power at the time t is going to be equal to Q all over 2 dV all over dt at that time t, and this is Q at the time t, plus V all over 2 dQ all over dt at the time t. So now let's visualize capacitors in circuits. Capacitors in circuits, the first point to note is that when you have this circuit here, you see the voltage here, the voltage is going to be, total voltage is going to be the sum of the voltage on the different capacitors. So V is equal to V1 plus V2. Now since V is equal to V1 plus V2, here V now is going to be, you know that V is equal to Q all over C. So this formula can be changed to be Q all over CT is equal to Q1 all over C1 plus Q2 all over C2. But we need to know that the current in this circuit is similar. Since the current in this circuit is similar, it implies that the charge in this circuit will be also similar. Since the charge in the circuit is also similar, we're going to have Q all over CT is equal to Q all over C1 plus Q all over C2. So I can cancel the charge all through. So 1 all over CT is equal to 1 over C1 plus 1 over C2. So CT is equal to C1 plus C2 all over C1 plus C2. So this formula is the formula for capacitors which are placed in series. And we realize that this formula for capacitors placed in series is similar to the formula of resistor placed in parallel. So now when capacitors are placed in parallel, you see that the current is going to be, the current here is going to be the sum of the two currents which are here. So I is equal to I1 plus I2. So it implies that the Q is equal to Q1 plus Q2. Since I is dQ all over dt, I multiply all through by t to remove the time. So it implies that we see that Q is equal to CV. When you substitute, it's going to be C total V is equal to C1 V1 plus C2 V2. But we know that in parallel, the voltage in parallel here, this V1 is going to be V and this V2 is going to be V. So when we substitute here, we're going to have C total V is equal to C1 V plus C2 V. So CT is equal to C1 plus C2. So now let's visualize for inductors. Inductors are circuit element that's going to reduce the sudden change of current in a circuit. And the EMF of the inductor is always given as negative L di all over dt. The current of inductor have already been found in the chapter on electromagnetism, and we said that the energy of the inductor is given as half Li squared. Now the power will be given as such. When we differentiate, we need to know that the current is the one which varies with inductors. So power is going to be half L di squared over dt. Differentiating this in relation to I, to differentiate this in function, so we are going to have half L 2I di all over dt. So the power at the time t is going to be the L at Li at time t di all over dt at the time t. So now let's visualize now circuits of inductors. Inductors in circuits, you need to know that when they are in series, V is equal to V1 plus V2. Now this V is going to be equal to L total di all over dt is equal to Li di all over dt plus Li2 di all over dt. But this I here is going to be same when same in series. So the I1 over the I over dt is going to be this, is going to be this. All this now are going to cause now the L total to be equal to L1 plus L2. So we realize that the inductance of inductors in series is the sum of the inductance, similar to resistors connected in series. Now in parallel, we see that I is equals to I1 plus I2, imply that di all over dt is equals to di1 all over dt1 plus that. So now when we substitute, we need to know that di all over dt is equals to v all over l. So you are going to have v all over L2 is equals to v1 over L1 plus v2 over L2. All this make the formula of the inductance, the total inductance in parallel, to be equals to L1 L2 all over L1 plus L2. And this is formula similar for resistors which are in parallel. Now let's visualize a circuit with multiple circuit elements. Circuit with multiple circuit elements. Now we are placed here. Here is a resistor capacitor circuit with a source. So we have a capacitor and resistor placed in series with a source here. So here the voltage of the source will be equal to V of the capacitor plus V of resistor. But V of capacitor, know that Q all over C, and V of resistor is equal to IR. So when we substitute, we know that at initial point in time, so the total voltage here is going to be the Q0, or the maximal voltage that is going to be drop on the capacitor divided by the capacitance. So when you have all this, you are going to substitute, where you know that I is equal to dq all over dt. We substitute it back here. So we are going to place now and form a differential equation. We are going to form the differential equation. We are going to differentiate both sides. We are going to integrate both sides. So we are going to have integral of 1 all over Q0 minus Q dq is equal to integral of 1 all over RC dt. You need to know that at start, or the time t is equal to 0. So at start, the time t is equal to 0 and q is equal to 0. So here you are going to have 0 and here you are going to have 0. And at the time t is equal to t, q is equal to q. So here you are going to have t and here you are going to have q, as shown here. So but the integral of 1 all over x equals to negative ln of x. So we are going to have negative ln of q0 minus q into this. All this is going to make you bow down to this formula here. So Q is going to be Q0 into 1 minus e raised to the power negative t all over RC. This is the formula for the charge on the capacitor. So the charge on the capacitor, in order for you to know the voltage on the capacitor, you just need to divide both sides by C. And the voltage of the capacitor is going to be given as V is equal to V0 1 minus e raised to the power negative t over RC. Now the current of the capacitor, the voltage on the resistor now is going to be the total voltage, which is V0 minus Vc. So when you do V0 now minus this formula here, we're going to have V0 e raised to the power negative t over RC. Now the current on this capacitor is going to be given as a differentiation. We need to know that current is equal to dq all over dt. So if I differentiate this formula, I'm going to bow down to this. I is equal to Q0 all over RC e raised to the power negative t all over RC. But RC is defined as tau, and this is the time required. Tau RC is defined as the time required for the capacitor to charge to 63.21% of the total voltage of the source. So since this is still defined as a time, I will substitute here as a time and say that Q0 over t is going to be equal to I0. So I, the current inside the circuit is going to be equal to I0 e raised to the power negative t all over RC. So now we have resistor capacitor circuit without a source. In this case, we're going to say that Vc is going to be equal to VR. It's going to be equal to negative VR. So now we are going to say that Q all over C is going to be equal to negative I all over R. So but we know that I is equal to dq all over dt. So we are going to have Q all over C is equal to negative R dq all over dt. All this will make you bow down in this formula here. We need to know that at start here, we are going to have at time equals to 0, the Q is equals to 0. So the capacitor, the charge on the capacitor at the beginning is maximal. So we are going to have 0 here, and we are going to have Q0 maximal. But the charge at the time t, the charge is reducing on the capacitor is reducing. So you start from Q0, then it reduces to Q. Here start from 0 to time t. but this is integral of 1 over x is going to give you this, and all is going to make you bow down to this formula. So cure is going to be cure 0 e raised to the power negative t over rc, and so v is going to be vc equals to v0 e raised to the power negative t over rc. The v of the resistance, we said that v of resistance equals to negative v of vc, so v of resistance also equals to v0 e raised to the power negative t all over rc. Now the current is the differentiation of the formula we had here of charge. When we differentiate with dq all over dt, differentiate this with respect to time, we are going to bow down to this formula here as being I0 e negative t all over rc. So now the next part is going to be resistor, inductor in circuit with a source. You have a resistor and an inductor with a source. Here v is equals to VL plus VR. So we are going to have here, we know that the I0R, I0 is going to be the maximal current in the circuit when the inductor stops functioning. So I0 times R is going to be the maximal voltage. This is the current in the circuit IR, and this is L di over dt due to the voltage of the inductor. So when you have this, we say that we place the di all over dt in one side of the equation. We are going to have integrating both sides. Integral of 1 all over I0 minus I di is equals to integral of R all over L dt. Upon having it, we need to know that at start, the current in the circuit is 0, and at time t, the current becomes I. So start from 0 here and 0 here and I to t here. So when you integrate, you are going to bow down to this formula and say that I in the circuit is going to be equal to I0 into 1 minus e raised to the power negative RT all over L. So now the V of the inductor is going to be given as V on the inductor is going to be given as L di all over dt. So I need to differentiate again this formula here. So when you differentiate di all over dt that you had here, you're going to have Li0 into negative R all over L e raised to the power RT. So it's going to end up by saying that VL is going to be V0 e raised to the power negative RT all over L. And the VR is V0 minus VL. So V on the resistor is going to be V0 into 1 minus e raised to the power RT all over L. So now in this case, now you have inductor capacitor circuit with a source. In case of inductor capacitor circuit with a source, you have V is equals to V of the inductor plus V of the capacitor. So Q 0 all over C is equals to L di all over dt plus Q all over C. So when you have this, you know that I is dq all over dt. So we are going to have a differential equation with a squared here. So since you have a differential equation with a square here, you're going to have L dq d squared q all over dt plus q all over c is equals to q 0 all over c. So this is the final formula you're going to have, and it resembles formula this form we are going to solve now a second degree of differential equation. Solving the second degree of differential equation is going to make us bow down to this first formula that we are going to have, and then bow down to this second formula we are going to have. All these are going to cause you to bow down to Q being equals to Q 0 e raised to the power t all over LC plus Q 0. So the formula for Q is going to be equals to Q 0 into 1 plus e raised to the power negative t all over LC. So now the voltage on the capacitor is going to be VC equals to V0 into 1 plus e raised to the power negative t over LC. And voltage on inductor is going to be negative V0 e raised to the power negative t all over LC. So now let's visualize now the last case, which is the inductor capacitor circuit without a source. In this case, we are going to say that VC is going to be equals to negative VL. And now we know that VC is equal to Q over C and VL is going to be di over dt. Now in this case, we are going to still have a solving of differential equation, a second degree differential equation. So d squared cure all over dt squared plus cure all over LC is going to be equal to 0. So we're going to say that solving this differential equation, we're going to say m squared plus 1 all over LC is equal to 0. When we bring it here, we're going to have plus or minus here r with an I here. So the formula is going to be Q is equal to a sine of this. So at the end, you are going to have this formula here. So the charge Q is going to be Q0 all over sine alpha sine of this. But now we need to know that the inductor and capacitors are from the AC circuit that you're going to study below here. The angle that exists between them is going to be 0, is going to be 90 degrees. Inductors and capacitors are going to exist at angle differentiated by 90 degrees. So the formula for the Q is going to be Q equals to, so the charge on the capacitor is giving us Q equals to Q0 cos of the square root of 1 all over LCT. The current in the circuit is given as I equals to negative Q0 all over the square root of LC cos of square root of 1 all over LCT. The voltage is just going to be this Q divided by C. It's going to be VC equals to V0 cos of square root of 1 all over LCT. The V on the inductor is the same as V of capacitor because there is no source in this case. So now the last case you're going to visualize here is a Kirchhoff law. And the Kirchhoff law, there are two main laws inside the Kirchhoff law. Number one law states that the algebraic sum of all the voltages in a loop is equals to 0, and the second, that is the summation of I equals to 0 to n of Vi is equals to 0. And the second law states that the current at junction split to give the respective current in the circuit. So we are going to use this diagram in order for us to have the different principles of Kirchhoff law. So principle of Kirchhoff law. To have the principle of Kirchhoff law, we have different steps. We have 5 steps involved. Step 1 of this diagram. In the step 1, we should identify the voltage which is highest. So identify the cell / battery with the largest voltage. So we should first identify, the first principle is that you should identify the cell / battery with the largest voltage. So when you've identified here, so that's the first step inside the Kirchhoff law. We see that the voltage with the largest, the cell with the largest voltage here is going to be this cell here. V is equals to 12 volt. That's step 1 completed. Step 2. When you've identified the voltage here, you can now draw current moving from that source. Since this has the highest voltage, then you can say that it is much more probable that it is going to be this particular cell here that's going to generate the current in the circuit. So I've identified step 1 tell me to identify the voltage or the voltage of the largest cell. Step 2 now tell me to draw current from that cell with the largest voltage. So the I is going to flow from the positive terminal of this cell outward as such here. Now if I find now I1 to and I2 to be negative, it implies that this direction of I1 and I2 on my diagram is supposed to be the opposite. But initially you are asked to find for the maximal voltage. When you find the maximal voltage of the cell with maximal voltage, then steps 2 tells you to find for the current direction from that maximal voltage cell. Now let's go to step 3. Step 3. In step 3 now, we are asked now to find, so in step 2 you see that this current I is going to split into 2, which is going to be I1 and I2, and this is the second law of Kirchhoff. At the junction, the current is going to split into the different part of the circuit. So I is equals to I1 plus I2. In step 3 you are required to draw loops, and the loops must be in the direction of current. So in conventionally by this book, loops are in the direction of current. So we have current here is going to split into I1 and I2, and this loop are in the direction of current. So we have loop A in the direction of current here, and we have loop B in the direction of current here. So in step 4 we are going to consider now loop A and loop B. So in this loop A, we need to note that since current flow in the same direction of the loop, it implies that the voltage that is going to be dropped on this resistor is going to be negative. So these are different principles that are going to be considered in step 4. Since current is in the same direction of the loop A, then the voltage drop on R1 is going to be negative. In this other case, since in this case now we see that the loop is moving from the positive terminal to the negative terminal of this cell here, so it is decreasing. It implies here that the voltage will be negative. VB is going to be negative. Now this R2, since current is in the same direction of R2, since current here is in the same direction as a loop flowing through R2, it implies the voltage on R2 is going to be negative. And lastly, as the loop come upward here, we see that the loop is going to move from negative to positive of this VA. It implies that the voltage of this cell here is going to be increasing from negative to positive, and thus is going to be positive. So this is going to be written as VA minus, because this one is negative, from moving from positive to negative, so it's going to be VA minus VB minus I1 R1 minus I1 R2. So this is I1 here and not I2. So now considering the next case, in case of loop B. In case of loop B here, you see that this I is going to move here. We are going to have here, since the I is going to be the same direction of loop B, then the current is with the voltage on out is going to be negative. Again here, since the loop is moving from the negative side to the positive side of the cell, then it's going to be increasing, and so the voltage VC is going to be positive. Since RC, since the current flow is in the same direction with the loop in RC, then the voltage drop on R4 is going to be negative. And here, since the voltage here is moving from negative to positive, then the voltage here is going to be increasing and thus positive. So the way to write is going to be VA minus, is going to be the VA plus, instead for this other case is going to be VA is going to be equal to VA plus VC minus I2 minus I2 alpha. So, and this other formula here. So there's a small error which is made on this Kirchhoff. So the main aim is to understand what the Kirchhoff states. So you're going to have, for this particular loop A, it's going to be VA minus I1 R1 here minus negative minus VB, and then minus I1 R2. So this is going to be equals to 0. So it's going to be negative V is going to be VA minus I1 R1 minus VB minus I1 R2 is equals to 0 by following the Kirchhoff first law. Now also this other law is going to follow still the Kirchhoff first law by saying that what you have VA, because this is positive, VA, you're going to say minus I2 R3. Here is going to be plus, because this is moving from negative to positive, plus VC, and here is going to be minus I2 R4 is equals to 0. So you have loop A and loop B being considered in Kirchhoff law. So from here we visualize all the different parts involved in direct current. I will say thanks for your kind attention. Please don't forget to like and subscribe for Science Makers. Thank you.